Now, for those of you who see force of gravity and you want to throw an mg, that's fine if you know what little g is, but we don't. So we're going to use the full formula. Big G, mass of Earth, mass of Moon, over that distance squared is equal to mass, which mass is this? On the right-hand side.
The mass of
The
the
mass of
moon.
the Earth.
The moon, right?
No, it's not the moon, the moon.
It's either Earth or Moon. Those are two choices.
Moon, because
Moon.
we're talking about the direction of the forces in terms of
We're
the moon.
trying to solve for the mass of the Earth, so it has to be
It has to be the mass of,
the moon.
yeah.
Okay.
Yeah,
Oh,
that's one of the reasons.
That makes sense.
And also, we're doing the equation of the moon right here. So this is the force acting on the moon. This is the mass of the moon.
What is that subscript under the A?
That's a C. And then I underlined it.
What is?
Centripetal acceleration.
Okay.
It's traveling in a circle. We are assuming a circle.
Which is v squared over r.
Yep.
Okay.
So ultimately, we're trying to find mass of the Earth. So let's just start canceling some stuff out first, just to make life
Yeah.
more convenient.
So we get rid of r at the
R.
bottom on the right, and then make that r squared into regular r.
Okay.
Cross out the mass of the moon.
So we get left with
GME over R equals V squared. Maybe.
All right. So mass of Earth equals v squared r over big G.
yeah.
So speed of the moon.
Do we know the speed of the moon?
Well, we can do that. Yeah, we have the.
Well,
How do you find speed?
It's centripetal.
displacement over the change in time.
That'd be velocity. How do we find speed?
Oh, because that's direction.
We just take out the vector.
Okay. But if we take the vector off displacement, what's it called?
Distance.
Yeah. Okay.
There we go, that's where we're looking.
So it's traveling in a circle. So what's the other word we have for the
Oh,
distance?
circumference.
Yeah. All right. So the speed is distance over time, which is our circumference there. So it's either pi r squared or 2 pi r. Which one is it?
2 pi r.
2 pi r, yeah. Man, y'all are good.
I heard confidence in both of those answers, so good with that. Over the period. So it's traveling one full circle in our 28.5 days, or whatever it happens really is. But we need to, come up with a common unit system here. Oh, what the heck? Let's just use the international standard.
Seconds, right?
Yeah, in seconds.
Okay, give it
Oh my gosh.
How many seconds in a day?
Oh gosh.
No, big number.
Like I think it's like
24 times 60
something.
times 60.
86,400. All right, I was way
So
off.
86,400 seconds per day. Day is going to cancel out, so I am left with seconds. So 28.5 times 86,400.
2,116,800.
Second.
That said. So the speed of the moon with respect to the Earth, 2 pi times my radius, which is 384,400,000 meters, divided by 2,116,800, or go to the other writing of it, 116. Using gaps instead of commas or periods, depending on how you were raised.
I got 1.14099,415. That's the entire number. Oh gosh, you want units? I know. What is this? Oh, units per second. Units per second.
Yeah, I think we're missing some other stuff there too.
Oh. Oh.
Radians?
Oh, gosh.
Pi.
It's not, it is traveling faster than I am traveling right now. I'm traveling probably about 2 miles per hour. which is about 1 meter a second-ish.
Yep.
I think it is traveling faster. If the moon travels faster than I can run, so
It's, you just moved it 3. It should be that.
So, 1,140 meters a second.
Yes.
That's what I got.
Oh, that was, wait, why?
What?
Was it just a calculation error?
Yes.
Yeah,
Oh, okay.
or a hearing issue, I'm not sure which.
I think it's just kilometers.
So we now have 1,140, you know, I think we could round here, 41 meters per second squared times 3.844 times 10 to the 8 meters divided by 6.67 times 10 to the negative 11 meters squared per kilogram squared.
That gives us the mass of the Earth. That should give us the mass of the Earth, right?
That's what I'm hoping.
Alright,
We should be at least within 10%.
let's see if I can not screw this up this time. Oh.
We're doing that.
I'm afraid to say what I got for fear of it being way off. I got 7.502 times 10 to the 24th.
7.502.
Let's go. It didn't seem right in my head.
Times 10 to the 24th
Yeah.
units.
Oh, that's where you got me. Oh, okay. There's a lot going on here. Oh.
It's gonna be kilograms.
Kilograms.
Yeah.
So you don't know.
That's why we put everything in terms of international standards, just so the answer would be. The more accepted answer is 5.98 times 10 to the 24th kilograms. So we're all farther than I expected.
It's kind of a lot off.
Oh, that was
5%
the-
off.
Dr. Fox?
This is actually closer to 27.3 days.
No,
I looked it up just now.
Yeah, I was gonna say, all those calculations for time of day was not 28.5.
It was very close to 20.
Oh, this right here?
Yeah,
Or it was
yeah, no,
days.
I know the 28 and a half days was off.
that's what I was talking about.
Okay, yeah. 27.3, 20, according to to IOP.org. 27 days, 7 hours and 43 minutes.
Yeah, those seconds right there, what we calculated for seconds is actually for 24.5 days for some reason.
Ah,
Yes.
Okay.
That's what I was referencing.
okay, that can explain several of these things. So if we do 27.3, what do we get here?
2,462,000.
2,460,000.
You doing 27.3?
Yeah,
Oh, sorry.
since we were here.
2,358,720.
Let's change this number down here. 2358720. Which changes that number there. Which changes this number here.
That is, do you want the answer to that
Yeah.
number? 1,023.969.
1024, rounding off. I still find that hard to believe it's gonna make up for the 25% off we are.
6.04.
Oh. Times 10 to the 24th?
Yes.
Okay.
I'm not sure
So,
that's right.
that made up for, well, that puts us a lot closer to this. Let's just assume that's right.
Yeah, I can
So-
do that on the test.
Pardon?
You can do that on my test.
I could. You know, if the answer was, if I got to 6.04 or 6.04 and you had 6.06, I probably would go, close enough on the test. Now, realistically, if we were trying to do this from, let's say, you know, a couple hundred years ago, and we couldn't look some of this stuff up, we could find the distance from Earth to Moon just by having two people look moons at a particular moment in time. We sort of figure out where we are on Earth and do some triangulation.
How would they communicate?
Pardon? How would they
Really
communicate?
fast pigeons.
Really?
I suspect that at the level of precision, you could just be on 2 hills and yell. Or flash the light, since light's traveling much faster.
Yeah, oh, yeah, I was about to say, how would they know, like, if one is measuring at 12 at their time, like where the moon
Right.
is right up, and then the other one does that, then like, how do they know, like, when the moon is directly overhead the other person? Or?
Yeah, well, I
when
mean,
the
you don't
time-
want, synchronize your watches. I mean, you potentially could, it fits on
17th century.
pre-mechanical watches or anything like that. That if you had, say, hour-long, sand clocks, that's the sand drips through, sand dial, no.
Sundial.
Hourglass, thank you, wow. It's only gonna get worse. All right. You each have a, I would say, an hour-long hourglass, and you make sure that they're both the same to start out with. You turn them over, and then you can travel out, so when the last sand drops, you do your measurement.
Okay.
I mean, there are definitely some extra error bars in there, but
Right.
it is a method. You do it over several nights and
Yeah.
pick the answer you like the best.
So the uncertainty's gotta be like massive.
It's like Galileo, when he was trying to figure out the speed of light, he was on one hill, his compatriot was on another hill, and he flashed the lantern, the person saw the lantern, he flashed it back, and they timed how long that took. And then they moved farther apart and did it again, figuring that the reflexes would be the same time. But came to the conclusion that if light is not infinitely fast, it's very, very fast. So,
I'm glad
I
they
mean,
came.
honestly, with what they had back then, that's pretty good
Respect.
conclusion. That's a respect there.
all right. So we've got just a couple minutes left. I am gonna do one thing and then we will go. There is a video for this, but I am going to do the quick and dirty derivation of one of Kepler's laws. It's definitely not the official one. I am going to assume circular orbit. Recognize that what we have here for my speed is just distance over time, so it's 2 pi r over t, so as I have written right there. So I'm going to use that formula right there in this. So I have g times the mass of whatever the central object is, so I'm just going to put mass sub c for central, over r squared equals, we will have, actually, we got rid of one of the r's there, over, is equal to v squared, which is just 2 pi r over the period squared. So basically taking the reduced form of this, so we got rid of one r and the mass of the moon, or whatever the orbiting object is. and then plugged in our general formula of distance over time from V. I'm now gonna square everything inside there. So I have G, mass of the central object, over the distance between the central object and the orbiting object is equal to 4 pi squared r squared over t squared. Because I know where I'm heading, I'm gonna bring r over to the right, take the 4 pi squared over to the other side, and I end up with G, mass of the central object over 4 pi squared is equal to r cubed over t squared. So what we have here is on the left-hand side, we have the gravitational constant, we have the mass of the central object, so for example, the sun. Mass of the sun is not changing appreciably within our lifetime, over 4 pi squared, which is also a constant, so this is all constant. So for all objects orbiting the same central body, this ratio of the distance, the average distance, cubed, between the orbiting body and the central object, divided by the period of the orbit squared, is the same. Yes?
How'd you get the 4 pi squared down there?
I hit period here, when I squared the whole thing, the period became squared.
Yeah, but like, how did you move the 4 pi squared under the
Oh,
G
oh.
of C?
I got two fractions equal to each other, I could move things across the diagonal.
Uh,
Or mathematically, I divided both sides by 1 over 4 pi, multiply both sides by 1 over 4 pi squared.
Okay. And you just move the R up there?
Yeah, and then
Okay.
multiply both sides by r.
Yeah, alright.
So this is one of Kepler's laws, I can never keep track of which one is which, I think this is the second one, but, yeah, I think the first one is things travel in an elliptical orbit. But this is one of the results of 40 years of Kepler's life.
Oh.
But you can watch the videos and do it all in a day.
Which is insane, can I say? I always think about that, how like, people spend thousands of years figuring all this stuff out, and we can just hop in the classroom and do it.
Yeah. Now, in defense of Kepler, calculus had not been invented yet. That would show up 100 years later. One of the reasons why Newton's laws were accepted so quickly and why that really became known is the fact that you could derive Kepler's laws from it. So if Kepler had not come first, it would have taken longer for that Newton's laws to be accepted.
But he crawled so that Newton could walk.
Yeah, as Newton said, the reason he saw so far is because he stood on the shoulders of giants.
Shoulders of what?
Giants.
That's how I feel, low-key. We could do I could build a car in 5 years. But that's not because I sat there and figured out all these numbers.
And I can do E equals MC squared because someone else has already done it. I can follow along.
Right.
It's
Yeah.
that blind faith of, this is gonna lead somewhere. Let me just go down this path and see what happens.
Right.
Anyway, I hope you all have a pleasant afternoon. And I will post the lab that, I think I'm deciding which lab we will do now. But I'll post the lab and please print it out before Wednesday. And you had some extra questions.
Yeah.